Hello everyone. In today's lecture, we'll be taking the example how we can control the lateral directional dynamics of an aircraft using backstepping based control. And also we'll have the MATLAB simulation for the same. So let's start the example. First, let me write down the equation of motion of the lateral directional motion dynamics. Example, let us consider the simplified lateral directional motion dynamics of an aircraft. We can write as beta dot, which is basically the side slip angle, y divided by mv minus r plus g by v sine phi. We are taking the simplified model, but you can take the complex one. So, and based on which the control algorithm also will differ, but the process of designing control will be same. And p dot equal to l ixx minus ixg divided by ixx r dot, and r dot equal to n by igg minus ixj divided by igg p dot, and phi dot equal to p. So this is the dynamic model of the lateral directional motion. And let us define the parameter here and the states. So here beta is actually side slip angle. P is the roll rate. R is yaw rate. And phi is the roll angle. And Y is the side force. L is yawing moment. And L is the rolling moment. This mistake. This is rolling moment. And N is the yawing moment. And M is the mass of the aircraft, total mass, and V is the velocity of the aircraft. So here we are assuming the expression for L, Y, and N as, so these are the forces and moment. So here let me define for simplicity. Let's consider. So here Y is half rho V square is Cy, and where Cy we can define as Cy beta, and Cy dr, delta, and delta. This is basically the radar deflection input delta, and also you can define L equal to half rho V square S B CL, and here CL we can write CL beta plus CL PP and CL delta A and delta A. And N you can define as half rho V square SB Cn, where Cn can write Cn beta, beta plus Cn RR plus Cn delta, delta. Okay, so here, so these are basically for total force and moments acting on the system. And here we can define delta R is the basically aileron deflection, and due to which the moment can be generated. And this is basically control input for roll angle. And we are assuming delta R be the rudder deflection input, rudder deflection. And this deflection can be achieved through the control, right? So this is basically rudder deflection. We can say control input or yaw angle. So this is how we can define the dynamics of this system and on which we'll be designing the control. So our objective is control objective. And design the control. So if you notice here there is two control input. One is delta R and is delta A. And but if you want to design both the controls, so you have to go a little long mathematics. But in this lecture, we'll be considering only delta A, which is going to control the phi angle. But also you can go the same step to design the delta R and to control your beta angle also, right? So the same process you can follow what you're going to follow for delta A. So our control objective is design the control delta A such that phi tracks the desired phi. This is a very interesting problem because we are going to track particular value of the desired trajectory. So let's start the problem, solving the problem. Solution. So first let us define the tracking error because we have to track the particular trajectory. So we need to have the tracking error. So tracking error, let us define tracking error for roll angle. We can write G1 equal to phi minus phi desired. And the dynamics for G1, we can write G1 dot equal to phi dot minus phi desired dot. So here, phi dot we have given here. This is the phi dot. So we simply write here, we can write P minus phi dz dot. So here, if you, the way you have done in the previous lecture, so P can be assumed as a virtual control for G1, which can be denoted as alpha or lambda, whatever whatever parameter it is up to us. So let P for as a virtual control input or G1, and this virtual control be defined as alpha 1. So here alpha 1 we can choose as minus k1 G1 plus phi d dot. So let us define, this is the equation number 1 and this is 2. The same steps we are following what you have followed in the earlier lecture. Now combine equation 1 and 2, combining equation 1 and 2, we can write G1 dot equal to minus K1 G1 plus P minus alpha 1, right? So this is, let us define, this is equation number 3. Now let us consider the Lyapunov function B. So Lyapunov function we choose to analysis on stability of the system. So let us choose B1 equal to half G1 square, and B1 dot we can write G1 and G1 dot. In place of G1 dot we can substitute this expression 3. So G1 we can write minus K1 G1 plus P minus alpha 1. And let us define this equation number 4. Now, if P equal to alpha 1, we can say B1 dot equal to, we can write minus K1 G1 square. So this is basically, it is basically stable. So the total energy is taking over time. So it is basically negative definite. So over time, V1 is decaying. So here it's stable. So now also you can find for this condition, for particular this condition, we can come up the expression for G1 dot. So from equation 3, for P equal to alpha 1, from equation 3, we can write G1 dot equal to minus K1 G1. So here K1 is positive gain, control gain, and we can say this is asymptotically stable. So now we have come up with the conclusion on G1 dot, and it is found to be stable. Now we'll work on G2. So G2, as you have done in the previous lecture, the error between P and alpha 1. Now the error between, why you are doing this, this is also we have explained. Alpha 1, sorry, alpha 1, we can write G2 equal to P minus alpha 1. And the dynamics for G2 can write G2 dot equal to P dot minus alpha 1 dot. In place of P1 dot, we can substitute this expression. This expression we can substitute. So P dot we can write as L minus Ixx minus Ixg divided by Ixx. So one thing, this Ixc actually product terms of inertia matrix, of diagonal terms you can say, and this is the diagonal elements. And here we can write this is R dot and minus alpha 1 dot. Now we have to choose, so we can write the L expression. So we have already L equal to half rho V square is P and CL beta plus CL beta and CL P plus CL delta A. This is already have. So now we have to choose delta A in this expression in such a way that J2 dot is stable. So what you're going to do is, so first let us substitute this expression L in this expression. So we can denote this the equation number 5. So now we can, from equation 5, we can write from equation 5, we can write G2 dot equal to half P V square SP CL beta beta is plus CLP P plus CL delta I whole divided by IXX minus IXG divided by the rest of term as it is R dot minus alpha m dot. And let us define this equation number 6. Now here we have to choose this delta A in such a way that G2 dot is stable. So here let us choose delta A as delta A equal to 1 upon CL delta A minus CL beta minus CL PP plus 2IXX divided by rho B square is B and minus K2 G2 plus IXG divided by IXX R dot plus alpha 1 dot. So this is the expression delta A, and if you substitute this delta A in equation 6, we'll have the stable function, stable dynamics for G2 dot. So let us define this as equation number 7. And so now substituting 7 in equation 6, we have G2 dot equal to minus K2 G2. And so we have the stable dynamics for this. So we can say this is here also K2. Okay, one thing. So here we have introduced new term here, this part, which basically gives this parameter, this values actually. And so here we can write, here basically we can say K2 is greater than 0, greater than 0. Yeah. And this is basically, we can say, asymptotically stable dynamics. So now we'll come up the Lyapunov function to prove the overall stability of the system. So let us choose the Lyapunov function as, now let us choose the Lyapunov function as V2 equal to half G1 square plus half G2 square. Okay. So this is basically nothing but the V1, what you have done in the previous. So here, if we take the time derivative of V2, so V2 dot equal to, we can write G1 dot plus G2 and G2 dot. And G1 dot, you can use this expression for G1 dot. So we can write here. So G1 dot, you can write G1 dot equal to K1 G1 plus G2, because P minus alpha 1 is G2 already have defined. So we can write here G1 equal to minus K1 G1 plus G2. The same process what you have done in the earlier lecture for the longitudinal motion dynamics. And here also same, J2 equal to K1, K2 G2. You can write. And from this you can write minus K1 G1 square plus G2 G1 G2 and minus K2 minus K2 G2 square. Now we have to work on this parameter, this term. So here already we have the fact. So using the fact is we have G1, G2, we can write half G1 squared plus half G2 square. So if you use this in place of G1, G2, if you substitute this parameter, we can write B2 dot equal, we can write, it is not equal to, we have to now use this less than equal to, because we are going to substitute this term. So we can write minus K1 G1 square plus half G1 square plus half G2 square minus K2 G2 square. And from this again we can write minus K1 half G1 square minus K2 half G2 square. And if you choose K1 is greater than half and K2 greater than half, so it will give us yields the overall asymptotic stability of the overall system. So we have done the control design of the entire system. And since our only objective to control the phi angle, so similarly we can use the, if you want to design the delta R, so we can proceed the same steps to design delta R for controlling beta angle. So now we can go to the MATLAB part here. So I'll go step by step. So we have initialized the total mass 1000 kg, and these are the inertia parameter. This is the rho in the dynamics, and basically in the density or density. V is, we have assumed 50 meter per second, and wing area is 20, and wingspan 5 meter. And these are the coefficient force, rather than roll moment and force coefficient we have defined here. And these are the other parameters what we have used in the dynamics. It's defined here. And we have choose the control gains, this K1 to be 2 and K2 equal to 3. This is which satisfies this condition also, right? This satisfies this condition. Now, these are the initial conditions for the states to solve the dynamics. And this is the desired trajectory of phi d and phi d. And this is the simulation time total 20 seconds. And we have used the OD solver to solve the dynamics. And here, this is the commands for the plots, figures. And this is here, this is the dynamic equation we have written here. So the aircraft dynamics is here. So we have defined the defined state by the x1, 2, 3, 4 like that. And this is the desired roll angle and its derivative. We have defined like that. This is basically the storing parameters. We're going to store the values in this parameters. And this is the error variable, whatever we have obtained through the analysis. This is the control control signal, what you have obtained through the analysis, delta I, equation 7. It is written here. And this is the total force and moment using the different force moment coefficients, which is basically this thing we have defined there. And this is the overall dynamics of the system. Now we have this is the MATLAB results, and we can see that our objective is fulfilled. So this roll angle is tracks the desired trajectory over the time, even it is achieved within 2 seconds. So though the simulation time for 20 seconds, and these are the result for the other states, and it is also controlled. So this is how we can design the backstepping control for this system. But this is the continuous code. Don't worry. Since this is difficult to capture in the one window, so I have taken differently. But this is a continuous code. If you want to write this code in your MATLAB window, you can use continuously. And so now we are going to start new topic from now on. So it is the last lecture in backstepping control. I hope you can design the same thing for your system, whatever system you are handling. If you have different dynamics, you can move on the same steps to design the overall control for the system. Even if it is spacecraft or other domain in flight mechanics or robotics, you can proceed with the same steps to design the controls. So let's stop it here. We'll come up with a new topic, sliding mode control from next lecture onwards, and we'll see how can design for the aircraft applications. Thank you.